In this video, we'll continue our exploration of graphs of polar equations. So we've looked at a few different types of polar curves at this point. We've looked at various types of circles and spirals. We've looked at limesons. And in this one, we'll look at what we will call polar roses and lemniscates. So we'll quickly review the types of polar curves that we've looked at up to this point. We'll graph one, and then we'll also learn about symmetry, which will be a very useful tool for us to graph any given polar curve. So first, some common polar curves. Circles and spirals we've looked at already. So we've got equations like r equals a gives us a circle, r equals a sine theta, r equals a cosine theta also gives us circles, r equals a theta gives us a spiral, kind of starting at the center and working its way outward. And then theta equals a just gives us a line. We also have limesons, which are these kind of loopy or heart-shaped polar curves. So limeson with an inner loop has an equation that looks like r equals a plus or minus b sine theta or cosine theta, where a is less than b. When a and b are the same, we have a cardioid. When a is greater than b, we get this little tiny dimple as it approaches the origin. And then if a is greater than or equal to 2b, we have a convex limeson, which starts to look more like a circle. Okay, so we will graph r equals cosine 2 theta. So if we think back a little bit to when we were graphing trigonometric functions with different periods, when you see cosine 2 theta, that should make you think that this particular graph is repeating itself twice in the domain 0 to 2 pi. So I want to start by graphing in rectangular cosine 2 theta. So we know we'll start at 0, we'll end up at 2 pi. We have pi, pi over 2, 3 pi over 2. Our horizontal axis will be theta, and our vertical axis will be r. Since we have no coefficient, since cosine is just being multiplied by 1, that means our amplitude will be between -1 and 1. And I think that's enough for us to start graphing our curve. So cosine we know starts at 1 when theta equals 0. That means it's going to go through one oscillation of the typical cosine curve in half the time, which means that we'll start at 1 at 0, we'll drop down to 0 at pi over 4, -1 at pi over 2, back to 0 at 3 pi over 4, and back to 1 at pi. Now if we keep going, it'll take the same shape, hitting 0 at 5 pi over 4, -1 at 3 pi over 2, 0 at 7 pi over 4, and 1 back at 2 pi. So in rectangular coordinates, the graph of r equals cosine 2 theta looks something like this. Just two oscillations in the domain 0 to 2 pi. So now to interpret this onto our polar coordinate plane, we'll try this one a little bit different to make sure that we're understanding how to map the graph of a polar equation in rectangular coordinates to polar coordinates. So we'll grab a couple different points here. We'll start with, maybe we'll call this 1 there. So we're roughly at theta equals pi over 6 there, which when we're at pi over 6, we'll be at roughly a half. So if we're at pi over 6, maybe we'll call this a half right there. Same point in orange. If we go to pi over 4, we'll be at 0. So pi over 4, we hit 0. We keep on going, we'll switch to green. Same kind of idea here. If we hit pi over 3, that should give us -1/2. So we trace over pi over 3, and then go down -1/2. Pi over 2, we get down to -1, right there. Then we keep going along. Maybe we'll grab purple. Hit a similar point at 2 pi over 3. So now we're negative 2 pi over 3, we go to -1/2. Now we'll start back at red. 3 pi over 4, we go back to 0. Okay, so maybe you can kind of see the pattern here. So we start at 0 and we trace kind of around and in. Then we loop around and back into the origin. We keep going, looping around like this, and then out to pi at 1. Then we conclude at 1 when we finish. Then we conclude with theta equals 2 pi, back at r equals 1. So it happens that there's a nice pattern whenever we see a number in front of theta. And it kind of looks like this. Some more common polar curves. So these are roses. With r equals a sine n theta or r equals a cosine n theta, the rose is n-leaved if n is odd, and 2n-leaved if n is even. So a couple examples, if we have r equals a cosine 2 theta, we have a 4-leaved rose. If r equals a cosine 3 theta, we have a 3-leaved rose, since 3 is odd. If r equals a cosine 4 theta, we have an 8-leaved rose, because n is even, we have a 2n-leaved rose. And then if r equals a cosine 5 theta, we have a 5-leaved rose. Step forward from that is a lemniscate. If we have an r squared equals a squared sine 2 theta or r squared equals a squared cosine 2 theta, we have these figure 8 shaped curves. So the last piece of this video is symmetry. So we have a few tests for symmetry which will help us to graph any given polar curve. Number 1, if the equation is unchanged when theta is replaced by negative theta, the graph is symmetric about the polar axis. So that should make you feel like we're talking about even-odd graphs. If you remember when we've talked about that, you know, if a graph is even, if you plug in negative x, you just get the function back out, right? That kind of thing. So if the equation is unchanged when theta is replaced by negative theta, in other words, the top half and bottom half are reflections of one another. Number 2, if the equation is unchanged when r is replaced by negative r, or theta by theta plus pi, the graph is symmetric about the origin. That is, two angles that are pi units away from one another take on the same value, the same distance from the origin. And lastly, if the equation is unchanged when theta is replaced by pi minus theta, the graph is symmetric about the line theta equals pi over 2. So now we kind of have a left and right half symmetry. So we'll just use symmetry to graph cosine 2 theta. So we'll try a couple different tests which will help us graph r equals cosine 2 theta. So first let's see if it has symmetry about the polar axis. So I'll give that a 1 from the slide before. So if we plug in, we're going to replace theta by negative theta. So we plug in r equals cosine 2 times negative theta. And this is just cosine of negative 2 theta. And since cosine is even, this is the same thing as cosine of 2 theta. So this says we have symmetry about the polar axis. Polar axis. Now let's replace theta by theta plus pi for the second part. So r equals cosine of 2 times theta plus pi. That equals cosine of 2 theta plus 2 pi, which then by addition and subtraction formulas, this is cosine of 2 theta cosine 2 pi minus sine 2 theta sine 2 pi. And that second term goes to 0 since sine of 2 pi is 0. And cosine of 2 theta times cosine of 2 pi is just cosine of 2 theta. So this graph also has symmetry about the pole, or about the origin. And then lastly, I'll just delete these. So we have 1, check, 2, check, and then to find out if we have symmetry about the line theta equals pi over 2, we replace theta by pi minus. So this gives us cosine 2 pi minus 2 theta. We expand that so we get cosine 2 pi cosine 2 theta plus sine 2 pi sine 2 theta. Again, the last term goes to 0, so we just have cosine of 2 theta. So interestingly, r equals cosine 2 theta has symmetry about the polar axis, about the origin, and about the line theta equals pi over 2. So what that says is essentially we could just graph the first part, 0 to pi over 2, and then do all the necessary reflections. So again, we would start at theta equals 0, which gives us 1. As we leave 0, we drop down to 1/2 at pi over 6, or right here, and then we hit 0 when we're at pi over 2. As we leave pi over 2, as we keep going, 5 pi over 12 gives us a negative 1/2 right there, and then pi over 2 gives us negative 1. So this is the first part of the polar graph of r equals cosine 2 theta. And then we can use all this other information to put it all together. So we have symmetry about the line theta equals pi over 2 and the polar axis, which can tell us that we can flip it kind of over the y-axis if we visualized y-axis there, as well as over the x-axis if we visualized an x-axis there. So altogether, that gives us the remaining bits of information. So we end up with our little rows. In the next video, we will start to look at the polar form of complex numbers and De Moivre's theorem.